Let's look at OpenStax University Physics Volume 2, Chapter 10, Problem 75. Consider the circuit shown below. What is the energy stored in each capacitor after the switch has been closed for a very long time? So let's look at the circuit. There is a power supply giving off 12 volts. There's a switch here. We have a resistor, and then this current is going to be split up into two currents, each one going through one of these branches. Then the current will meet back up over here and form the original current that started out from the battery. So what that means is that these two are actually connected in parallel. So we have this branch connected in parallel to that branch. So we want to find the energy stored in each capacitor after the switch has been closed for a very long time. But first, let's see what happens when we first close the switch. So at t equals 0, we know that when the switch closes, current will flow from the battery to the resistor, and then it will split up. Part of it will go through the capacitor, which is completely discharged. So the capacitor will act as a wire at that point, and then it will go through the resistor R2. Then down here, it will go through the resistor R3, and it will pass through the capacitor as if the capacitor isn't even there, because the capacitor at first acts as a wire until it starts building up charge on it. So we have this circuit at time equals 0. Now, a long time later, so when the capacitors have a chance to charge, so I'm going to call this t equals infinity, we have the battery, we have the resistors, so here is R1, and a long time later, the capacitors act as a broken wire. They no longer let current go through. So this would be R2, this is R3, and again, the capacitor acts as a broken wire. It doesn't let current go through anymore, and we end up with this circuit. Now, if we follow the current goes through this point, and then there's a broken wire there, there's a broken wire there. There is no closed loop here for the current to go through. So that means that there is no current going through resistor R1, R2, or R3, but the capacitors are fully charged. So that means that each of these capacitors actually does have charge across the plates. So there is a Q1 and a negative Q1 here. So it's plus Q1 on the left, negative Q1 on the right. And there is a Q2 and a negative Q2 on the second capacitor. So they break the wires, but they do have charges on them. And when they store charges, that means that there's going to be energy stored in them as well. So what happens now is that since there is no current going through here, the voltage across this resistor is 0. There's no current going through there, the voltage here is 0. Same thing there, voltage is 0. So what we end up with is essentially capacitor 1 in parallel with capacitor 2, and all the voltage supplied by the power supply is across the capacitors. So this is our 12 volt, and here are the capacitors with charges on them, fully charged. And there is a voltage across them. So we can solve then for the energy. Energy is 1/2 CV squared. So the energy stored in capacitor 1 is 1/2 C1 V squared. So that is 1/2 C1 is 10 millifarads, 10 times 10 to the negative 6 farads, times the voltage, which is 12 volts, and we have to square that, and we get 0.72 joules. For the second capacitor, then U2 is 1/2 C2 V squared. So that is 1/2 times 4.7 times 10 to the negative 6 farads times the 12 volts squared, and that is 0.34 joules. So something very important to know for capacitors is their behavior at time equals 0 and their behavior at time equals infinity. At time equals 0, an empty capacitor will start charging, and first it will act as a wire. At time equals infinity, long time later, the capacitor is fully charged and it breaks the circuit. It lets no current go through anymore.